Go is a language built for clarity, one way to do most things, and a compiler that refuses to let ambiguity slide. In this video we'll walk through 6 core lessons from Level 1 of the Go Mastery Path: variables and types, control flow, functions, collections, structs, and pointers. By the end you'll see how these pieces click together into real, idiomatic Go code. Let's start with how Go stores data. Go is statically typed, but it infers types for you most of the time, and it never converts between types silently. Inside a function, the short declaration is the idiomatic way to create a variable. Go looks at the value on the right and figures out the type for you. Var is what you reach for at package level, or when you need a specific type that inference would get wrong. Here's something that trips up newcomers from other languages: a declared variable in Go is never left undefined. Every type has a 0 value, 0 for numbers, an empty string for text, false for booleans, and nil for slices, so your program is always in a valid state. Go's basic types cover integers, floating point numbers, strings, a rune type for single Unicode characters, and booleans. Int is the general-purpose choice, size to match your platform reach for a specific width, like int64, only when the exact size actually matters. For related constants, Go has iota. It resets to 0 inside a const block and increments by 1 each line, which makes it the standard idiom for building a small enum-like set of values, like a status, pending, active, done. And because Go never converts types implicitly, mixing an int and a float 64 in the same expression is a compile error. You convert explicitly, which feels strict at first, but it means a whole category of subtle bugs simply can't happen. Once you're comfortable with types and constants, the next question is how a program makes decisions. That's control flow. Go keeps control flow deliberately simple. Braces are mandatory around every if and loop body. There's no one line if without them, and there's exactly one looping keyword, for. A standard if, else chain looks almost like any other language, just with mandatory braces and no parentheses required around the condition. Here's a distinctly Go idiom: an if statement can run a setup statement first, then check its result, with both scoped only to that if and its else. You'll see this constantly with functions that return a value and an error together. For covers every looping style. Other languages split across for, while, and do while, a classic 3-part loop, a while-style loop with just a condition, an infinite loop you break out of, and range, which walks a slice giving you the index and the value. Go switch doesn't fall through by default, each case just breaks automatically, the opposite of C or Java. You can switch on a value, or write a switch with no expression at all, which reads like a clean if-else chain. With decisions and loops in place, the next step is packaging logic into reusable functions. Functions in Go have a signature feature: they routinely return more than one value. That single idea shapes a huge amount of idiomatic Go code. Here, divide returns both a float 64 result and an error. The caller checks error immediately. There's no exception to catch, just a value you're expected to look at. Return values can also be named up front, and a bare return sends back whatever they currently hold. Divmod uses this for quotient and remainder. It's handy for short functions, though overusing it can hurt readability in longer ones. Variadic parameters, marked with 3 dots, accept 0 or more arguments collected into a slice. You can call some with individual numbers, or spread an existing slice into it using that same 3-dot syntax. Functions are also values in Go. You can pass them as arguments or return them from other functions. CounterFrom returns a closure that captures its own count variable, so each call to next remembers state between calls. And defer schedules a call to run right before the function returns, no matter how it returns. It's the idiomatic way to keep cleanup code sitting right next to the resource that needed it, and multiple defers run in last in, first out order. Functions give you logic and reuse next. Let's look at the data structures you'll actually be passing into them. Go has 3 built-in collection types, but in everyday code you'll mostly reach for one of them: slices. Arrays get a mention too, though you'll rarely reach for them directly. An array's length is baked into its type, so a 3-element array and a 5-element array are actually different types entirely. That rigidity is exactly why slices, which are more flexible, are what real Go code reaches for instead. A slice literal works the way you'd expect, and append grows it, returning a possibly new slice. Slicing with a low and high bound pulls out a subrange. The high end is exclusive. Here's the part that catches people off guard: slicing doesn't copy data. Two slices can point at the same backing array, so mutating one through its shared view mutates the original too. If you need an independent copy, that's what the copy function is for. Maps store key-value pairs, and reading a missing key silently returns the 0 value, so the COM-OK idiom, where you check a second returned boolean, is the only reliable way to tell key present with a 0 value apart from key absent. Slices and maps hold your data. Structs are how you give that data shape and identity. A struct groups related fields into one named type Go's version of a lightweight class body, without inheritance. You can build a struct with named fields in any order, positionally if you match the field order exactly, or leave it 0 valued and fill it in field by field afterward. This next part matters constantly. Structs are value types. Passing one to a function copies it, so try to modify here only changes its own local copy. The caller's original point is completely untouched. Go's alternative to inheritance is embedding. Dog embeds animal, and that promotes animal's fields and methods straight onto dog. You can call d.speak directly, with no need to write d.animal speak. Since structs copy by value, there's an obvious next question: how do you actually let a function change the original? Pointers. A pointer holds a memory address instead of a value. Go's pointers are safe, no arithmetic like in C, and the garbage collector always knows what they point to. The ampersand takes the address of a variable, and the asterisk dereferences a pointer to get the value back. Writing through the pointer actually changes the original. Set the dereferenced value to 100, and x itself becomes 100. Remember how passing a struct by value copies it? Here's the fix: movePoint takes a pointer to point, so it reaches back into the caller's actual struct instead of a copy. This time, the original really does change. A pointer's 0 value is nil, and dereferencing a nil pointer panics at runtime. So idiomatic, Go code checks for nil before it dereferences anything that might not be set. One last wrinkle worth knowing: slices and maps already carry an internal pointer to their data, so passing them by value still lets a function mutate their contents directly. No explicit pointer required. That covers the core of Go's Level 1 fundamentals: types and constants, control flow, functions with multiple returns, slices and maps, structs, and the pointers that let you mutate them. Every lesson we covered is linked below if you want to read the full text and try the exercises yourself.